Printing process and parameters to buildability to microstructure to hardened state properties to layer effects, mechanical properties, compression, flexure, all of those we have seen. Eventually, we look at durability, which is the later age performance. The only difference here is the layer induced effects. The rest of it is exactly the same properties that influence durability of conventional concrete. So the layer effects, because of the higher porosity in the layers, like you saw yesterday, that's an effect that you will have to address to make sure that the 3D printed structure is durable. But again, depending on what kind of reinforcements you use, how you use it, that's one thing. And then the other issue is that the lack of formwork exposes so much of surface area. The surface area to volume ratio is very high. That influences shrinkage and cracking. So those are the two major durability issues. You will have people looking at freezing and thawing. You have people looking at acid attack, people looking at sulfate attack. All of those will exactly be same as conventional concretes. You will have zero difference. You should have zero difference, right? Those are all basic concrete properties itself. So we look at a few durability characteristics and see what happens. Shrinkage and cracking is one of the bigger concerns. So here is a shrinkage crack that has completely gone through, and here are smaller shrinkage cracks that are distributed across layers. You also saw some of shrinkage cracking in the printed layers yesterday. So it is obvious that when you have higher surface area, you will have shrinkage. So there has to be means and methods to control them. You see them covering the entire thing with gunny bags and spraying water all the time so that you can control shrinkage, right? So that's one thing. And then if you don't control it, the restraint will let it crack all the way through the structure. This will now, a crack of this level will start to influence the structural capacity as well. So balanced approach for service life, printability, extrudability, mechanical performance. That's what we have seen in the last 4 days. And then you need the durability characteristics. Synergistic effect needs to be considered like you need for every concrete. This is not typical for 3D printed concrete. For every concrete, you need to balance the mechanical properties and durability, correct? You have a requirement for certain mechanical properties. You need the structure to serve for a certain period of time. Your service life considerations, how long do you want? Now, if you are doing a temporary structure, if you're saying that, okay, I'm going to do this building until I finish my new fancy state-of-the-art building, there's going to be a temporary building. You don't design for 50 years, right? So you can afford to be a little more lax about the durability. Whereas when you're dealing with long-term structural life, you need to think about what levels of durability that you want. Now, lot of times in conventional concrete structures, reinforced concrete structures, your durability is strictly a function of corrosion of steel. If you're a reinforced concrete structure, your durability mostly is defined by corrosion. There is sulfate attack, there is ASR, there is acid attack, there are lots of other things. But in a structure that is in service, the one that really bothers you the most with respect to durability is not the problem of concrete itself, but the problem of putting steel in concrete, right? Reinforcement corrosion. The reason that really bothers all of us is because reinforcing steel, when it corrodes, expands in volume. That volume expansion causes tensile stresses. Tensile stresses causes cracking. Eventually, the problem is cracking and the cracking induced ingress of deleterious ions and all of those things into your concrete. So that's where you don't want durability issues. And then corrosion is also caused by chlorides that are going in. So if you don't make a good enough concrete that is porous, the chlorides will gradually find their way into steel much faster than you would do. Otherwise, you can solve Fick's second law of diffusion, find diffusion coefficient, find time required for chlorides to get to a certain point. You can do all of that, all solutions. So that's fairly well understood problem. Well understood, but not well solved. There are several different solutions for reinforcement corrosion protection, you can epoxy coat, you can galvanize, you can do all of that. You can have sacrificial anodes, you can have cathodic protection, lots of different ways in which you can protect it. But the fundamental first layer of defense is eat well and exercise. Correct? Like doctors say, best thing is to take care of your body well. And then if it doesn't work, you can take some medicines. Right? The first order of defense is to make sure that your concrete is well made, well taken care of, uh, good proper water cement ratio, good compaction, good curing practices, so that you can protect it against any kind of damage. So with 3D printed concrete, we won't talk much about corrosion because we don't really have enough data on corrosion of steel within concrete. If you watched carefully yesterday, did you see them placing rebar on the lintels when they were printing it? So they actually put rebar on the lintels because they were printing the lintels too. The tensile stress are going to be very, very low. So even if the bond between the steel and concrete is not very good, that's not a big problem there. It's going to be a very small structure. But when you get larger structures, some of those issues will become critical. Generally, we don't have much rebar in 3D printed concrete, so we don't really know about corrosion performance. We don't have that much of data. So we'll talk about reinforcing strategies in the next lecture. Generally, as to what are the potential ways to reinforce if you have to. But like we said, the best strategy is to make sure that you make use of compression of concrete as much as possible and not rely on tensile stress capacity. But when you do things like bridges, you will have to take care of tensile capacity. In that case, topology, form optimization, and using steel wherever you actually need them and protect the steel well is the only way of doing it. So same idea, get good quality concrete so that you can prevent the entry of deleterious ions. Near surface concrete quality problems are what lets chlorides and moisture get in and cause durability issues. So again, what happens when you print? You will have crack, exposure to deteriorating agents, cracks come in, all the chemicals come in inside, they'll start to react with things in concrete and start to break them apart. Very similar mechanism as you see. Now, this is something that we have seen yesterday, right? You have interfilament voids, you see here. So all these filaments coming together. So you have interfilament cracks and then you have interlayer cracks too, correct? So interlayer zones, all of these interfaces can create entry points for chemicals and deteriorating agents to come in. Porosity versus of mold cast versus 3D printed, we saw that yesterday. If it's mold cast concrete, your porosity is uniformly distributed throughout the specimen. In 3D printed concrete, you have layers or zones in which your porosity is higher. We showed that completely yesterday with respect to where you can see that increase in porosity, depending on how you look at it, both interlayers and interfilaments. Size of pores and voids in concrete. Again, this is generally in your regular concrete. You can have 9 orders or 10 orders of magnitude size in pores, correct? The really small pores in your CSH gel, the gel porosity as you would call it, which is also pores, all the way to entrapped air voids, larger air voids in concrete spans 9 orders of magnitude. So basically, if you want another example, that if you had seen a concrete textbook, they would show you pictures. The size is corresponding to the height of a man to the size of Jupiter or Saturn or whatever. Those are the size ranges of pores in concrete, and that eventually results in several different transport mechanisms. So if you remember some of your basic classes, you have absorption, you have adsorption, you have permeation, you have diffusion. Remember all those transport mechanisms? Depends on what are the size of pores that are influencing the process, and depending on whether it's a concentration dependent process or a pressure dependent process, these mechanisms differ. The mechanisms therefore influence how fast and how deep these ions go into concrete. So you have to think about all of these things in unison. You will have capillary voids, you will have entrained air bubbles, entrapped air bubbles. Now, what is it that we can definitely say exists in 3D printed concrete? The layer porosity, right? And the interfilament porosity that are like the entrapped air voids, larger air voids like we have seen. So we need to make sure that we have to control those voids. Okay, now different stages in transport. How do you look at if you have agents coming in? So think about different ways. One is if you have an agent coming through the surface this way, then you will have to initially deal with the bulk layer. You probably have a diffusion process, and then it finds a nice way to spread around and increase its concentration. So if you think about it, if you look at that way. If you look at this way, you will have direct paths of transport quickly, correct? Through the layers, your agents can move in. Remember, the size of a water molecule is about 18 angstrom, 1.8 nanometers, right? 1.8 nanometers is the size of water molecule. Typical pore that you have is 100 micrometers, 10 to 100 micrometers. 1.8 nanometers and 100 micrometers are 4 orders of magnitude different, right? For the water molecule, a 10 pore is like a superhighway to go through. So you can have very quick, very fast transport of materials through it. And as it comes through it, when you have enough of material that's built up in these layers, then it will start to move up and down in these layers also. So you can have these transport mechanisms happening in several different ways. And then if you have in porosity in between and these transporting materials interact with some chemicals within concrete and starts to crystallize again. For example, if you have gypsum crystallizing within, if you have ettringites crystallizing within at a later date, you will have expansive pressure, and even without more porosity, you will have cracking. So all of these mechanisms, like you have in normal concrete, you should expect in 3D printed concretes also. So you will have migration, diffusion, permeation, all of these processes happening together. Again, fundamentally because of the oriented porosity that you have. The one advantage that you can say, again, you'll have to think of your disadvantages as advantages somehow. One advantage you can think of is you can fairly reasonably predict the direction of transport. Unlike normal concrete where it could be really random, you can say, okay, which way this is going to go. So if you ever have to protect it with a sealant or a coating, you know exactly what to do, right? So that's an advantage if you want to think of it that way. But generally, the mechanisms of transport is like this. Effect of print parameters such as time gap on the porosity of printed concrete. So you can see printed at 0 minutes. Again, cold joints. You saw that yesterday. You saw them putting in little nails so that there won't be cold joints. When they stopped it at the end of the day, they were putting small nails so that when they put the next layer in, there is some level of connection and there is proper load transfer. If you put wet on wet, you really don't distinguish these layers. But if you have a cold joint, you can really see that. And along those layers, you have higher porosity. So higher porosity, the interface when you have a time gap, all of that. In those cases, you need to make sure that you have a way to improve your interlayer bond strength and improve the density of that interface, not to have enough porosity. What happens when water goes out of, again, standard concrete? Again, this really, there is nothing more different here. This is kind of exaggerating a few points that are relevant to 3D printed concrete. Otherwise, really nothing different in terms of mechanisms from conventional concrete. So here is water coming to the surface, capillary rise. Through a layer, capillary rise will be quicker. Remember, I showed you yesterday when water comes out, when there is a layer interface, there is a tendency for water to spread onto that layer. And very similar to the interfacial transition zone in concrete, which is porous, your layer is going to be porous there also. So you will have that layers. You will have a drying stage, and if the drying is non-uniform, you will have non-uniform surface texture. Next layer is placed, you may not have proper bond when you do it. So interlayer water revolution at the interfaces creates further further voids. Things that you will see only under a microscope if you look at after the fact. But if you know how this happens, you can control the drying process. You can make sure that you spray curing compounds. You can start curing all of that processes early. Pore structure and transport properties, again, nothing new here, exactly the same. Porosity is higher. Generally, when the porosity of concrete is higher, pore connectivity also is higher, right? We have difficulty generally measuring the connectivity of pores in concrete. We can easily measure porosity using something like a mercury intrusion porosimeter or even simple vacuum saturation methods. There are standard test methods. So measuring the porosity of concrete is not a big deal. We can do it. But porosity by itself is not the only factor that determines transport, but we can take comfort from the fact that as the porosity is higher, because I have generally distributed porosity, as the porosity becomes higher, the connectivity between pores also is higher. So, how many pores? So, here is a question. How many pores are there in concrete? If I give you a standard normal concrete, how many pores are there? How many pores are there? Just I'm not giving you size. I'm not giving. It's a very quick. You can easy answer. You can figure out from the question itself. I'm not giving you size. I'm not giving you volume. How many pores are there in concrete? A bulk. I'm keeping a concrete slab here. How many pores are there? Huh? That's porosity. How many pores? Hmm? Innumerable pores. Okay, that's one answer. Think of it a little more. Innumerable is an easy answer. What is the other extreme? How many pores? As many as, depending on how you look at it. But what if I say there's only one pore in concrete? At some level, everything is connected, correct? The level of connectivity could be different, but at some level, so this is from one of my professors, Sid Diamond. If you've heard about Sid Diamond, this is Sid's standard thing. Take any concrete, I can tell you how many pores are there, just one, right? So eventually, it's all the pores are connected. So the level of connectivity would be different. The porosity could be different, but the pores are all connected. And that is why we have transport of moisture and transport of all the other ingredients through from the surface, everything going in through diffusion, going through the level of rebar. So porosity and pore connectivity are the ones that are important. Porosity you can easily measure. Pore connectivity, we always had difficulty measuring pore connectivity, but right now with electrical impedance measurements, you can actually quantify pore connectivity. You can do beautiful imaging methods to do pore connectivity. There are beautiful methods where you can look at the connectivity of pores and start quantifying some of those. So remember the image analysis things that I've been telling you? So if you actually get a very nice microstructure of a material and then you stack, remember I told you you can make several different layers, stack those different layers, and if you create like in image J a three-dimensional microstructure and you say one face is pore, one face is solid, if you stack those microstructures, you can actually start to quantify numerically the connectivity of pores. So another nice way to quantify it. And any durability property is directly related to the connectivity of pores. The more connected the pores are, the less durable the material is going to be, whether it is corrosion of reinforcing steel or sulfate attack or any moisture-induced processes. Okay, so vacuum saturated porosity. So this is about vacuum saturated porosity at the interface is 10 to 16% higher than in mold cast concrete. At the interface, Obviously, right? The porosity will be higher at the interface. You can do mercury intrusion porosimetry. You can take a piece of concrete, cut it with an interface and the bulk, take a small piece from the bulk, do MIP, take a small piece from the interface, do MIP, you will see 10 to 20% of difference in porosity between bulk and interface. Interface are always more porous. You can quantify that. And therefore, the transport of moisture and ions through the interface will be faster or slower? Much faster, correct? So here is, and we'll talk about transport behavior that's also anisotropic. So we talked about anisotropy in mechanical properties yesterday. All three directions the properties are not uniform because there is layer effects, there is porosity, there is interface porosity. Because transport also is determined by porosity, therefore transport properties also will be anisotropic. So you will not, like your conventional concrete, core a cylinder from wherever, cut a piece from wherever, do an RCPT from wherever. The value that you get, 1000 coulombs, is the value of your RCP. No, it will be dependent on the direction in which the ions go through. Right? That's what I showed you. If I do a transport measurement through this direction versus transport measurement through this direction, they're going to be very different. This direction is going to be much higher than this direction, right? Because this direction, there's a significant amount of time it takes to get to this level, whereas here, there's a superhighway that goes through it. So transport also will be anisotropic. So here is some work. This is from Sahil's work on anisotropy in chloride transport. Different layer heights. Remember the differences in layer heights? Let me check how many people were actually paying attention yesterday. Because I actually drew those pictures here too, right? So if I have a smaller layer height, will my interface be better or worse? Better. Why is it better? Because I apply some compaction. If I have a larger layer height, will my bulk be better or worse? If I have a larger layer height, will the bulk be better or worse? Worse, because I don't have enough of compaction. So is it better to have more interfaces with a smaller layer height or fewer interfaces with a larger layer height? More interfaces with a smaller layer height. You guys seem to be listening. Surprising. Everybody seems to be awake. Good. So very similar idea. We are going to do the same thing with layer heights. 6 mm, 13 mm, 20 mm. And what do you expect? Actually, the answers are obvious. I don't know why Sahil did all this work. Okay? I mean, he just came in and said, I've done all this, let's publish it. And we did that too. But now looking back, was there a need for this work? Don't tell no, he'll be very upset. Right? But the answers are generally obvious, but there are some subtleties that we have to understand. But everybody understands the general idea, right? What will happen in a general way. Okay, so you take a cube and you core it in 3 different directions so that you get the anisotropic coefficients. You cut the cylinder into 50 mm thick discs. All of you know what rapid chloride permeability test is. All of you have done rapid chloride permeability, RCP, right? So this is, we can't do rapid chloride permeability, or we can do rapid chloride permeability, but then if the porosity is very high, RCP is not a good test, right? Because rapid chloride permeability measures the resistance when you apply a constant voltage of 60 volts. Resistance of what? Resistance of your concrete. But when you have so much of force that is connecting both sides of your solutions, what resistance are you measuring in that case? The resistance of that solution that goes through, right? So RCPT makes no sense when you have very highly connected pore structure and things that are so, and that's why when you have really porous concretes, your RCP value really doesn't make sense. You get a very high number, but it's a useless. I mean, RCP generally is not a good test. People are trying to understand and realize it now because you're applying an extremely high voltage over 6 hours. You have so much of heating effects. And resistance or conductance is a function of temperature. You're getting so much of Joule heating effects. And temperature changes the microstructure of concrete. So when you have an RCP test and when you have a very dense concrete with a very dense microstructure, which means the resistance is very high, the temperature also is very high. So when you get to about 80, 90 degrees Celsius temperature, when you do this test, you will have micro cracks that happen. Right? So it's actually not a good test. The better test that we do with respect to an electrical property test is what's called a migration test. And I'll show you that. Again, people are kind of changing it. You can do it with the same setup. You can do it with the same processes with slightly different way of doing it. So here are capillary porosities in different directions. Cast D1 and D2 direction. So you can see the difference in porosities. Not extremely high, but there are some differences in porosities in the different directions. You can also use, all of you know mercury intrusion porosimetry, MIP. Have you heard of this? So it's a technique where you introduce mercury under pressure into the sample. Okay. Now, mercury is what we call a non-wetting liquid, which means mercury is a liquid, correct? All of you know that mercury is a liquid metal, but it will not wet the surface, which means no, the surface of concrete will not absorb mercury. If I try to squeeze water into it and want to measure how much water goes in, I can't measure it because concrete absorbs water. Whereas mercury will not be absorbed. And so if I can squeeze mercury under high pressures into your concrete sample, mercury will go into all your pores. So if I start with certain amount of mercury, squeeze it into concrete, and then find out how much mercury is left, do I know how much mercury has gone into the volume of concrete? And if I know the volume of concrete that I put in, can I now know what's the volume of pores that the mercury has gone into? So that's a simple, very simple, oversimplistic explanation of what mercury intrusion porosimetry does. Now, the interesting thing is, how are you squeezing mercury into the sample? Under pressure. How much pressure? Ridiculously high pressures. 400 megapascal, correct? Close to 400 megapascal in the high pressure zone. 400, can you imagine 400 megapascal pressure? Really high pressure. And now you will ask, 400 megapascal pressure, my concrete will completely compress. Why is that not happening? Anybody wants to answer that question? Anybody who has done MIP? I'm applying a pressure. Your mercury intrusion porosimeter will show you a reading of 400 megapascal. And can any concrete sample withstand 400 megapascal stress? No, then am I measuring the porosity of a powder? What does that even mean? You said I'm measuring the porosity of a piece of concrete, and now you're telling me 400 megapascal. Hmm? What is that called? It is a hydrostatic pressure. It's under triaxial state of stress. And in materials that are under triaxial state of stress, you will demonstrate an extremely high apparent strength. That is why if you have done your geotechnical class, you never do a uniaxial compression test on a soil, because you can't do a uniaxial compression test on a soil. Soil is a granular material, it just compress and break away. But if I enclose it into a sleeve, all of you have done that triaxial test in soil, you enclose the soil in a sleeve and apply pressure from all three directions, right? Now you can measure what is the capacity of it. Of course, you will get two different stresses, your axial stress and the lateral or the dilatant pressure. Remember all of that? So same idea, the piece of concrete is actually submerged by mercury on all sides, and mercury is squeezing into it from all sides. Right? Therefore, you don't crush it, you actually squeeze mercury under a triaxial state of stress. Now, assume that I have, how many pores are there in my concrete? Totally one pore. Of course, we'll do differently, we'll count it differently, but eventually one pore. But are all the pores like one cylindrical, nice pore of the same size? No, they're all of different sizes. So when I have pores of different sizes in my concrete, when I squeeze concrete, so there's a very interesting idea called ink bottle effect. So think about it. If I'm applying pressure to squeeze mercury and assume that my pores are like this, and the the way that I squeeze them is using pressure, right? Correct? And pressure is inversely proportional to the radius of the size of the pore, correct? Which means the larger the pore, the lesser the pressure I need. The smaller the pore, the higher the pressure I need. So assume that I have a pore like this. Okay, so listen to this. This is very interesting, and there are reams and reams of papers written on this idea. Assume that I have, and so everybody who is using MIP should understand the inherent drawback of this method. So if I'm applying a pressure through this, what is the pressure that is required to get, say, this R1 is size of this pore? I need a certain pressure P1 to get to this pore, correct? So now there is a correspondence between pressure and radius. So if I measure the pressure, I use what is called the Washburn equation to find the radius, right? So I will now find out the radius from the equation. I find pressure P1. I know, oh, now my radius is R1. Will mercury go into this pore under that same pressure? No. Should I increase the pressure or decrease the pressure? Increase the pressure. Once I increase the pressure, I got to a pressure P2 to get to this pore R2. P2 is greater than P1. R1 is greater than R2, correct? Right? So I got to now this pore with a pressure of P2. So my porosimeter says, okay, now your pore size is R2. But then under this pressure, do I need any extra pressure to get to this pore? No. So what is the pressure under which mercury gets to this pore? P2. What am I thinking the size of this pore is? Is it R2? No, right? Suddenly you now lose the size distribution effect. You can't find out what the size is. So this is called the ink bottle effect. So mercury will go through all of this. So let us take this example. Now, if I remove the pressure, mercury has to come out, right? If I remove the pressure, it will come out of this pore at that pressure, and then when it comes out of this pore, it will just take this also because that's certain value, right? And then if there is another pore that is smaller, mercury will not come out of that pore if I further don't evacuate it at a higher pressure, which I cannot because I've already gone back into that pressure, which means mercury gets stuck in that pore. So when you withdraw the pressure, because the pore sizes are all connected and they are all different sizes, mercury may not come back out of all the pores, which means if I impregnate the sample with 10 milliliters of mercury, I might get only 7 or 8 back. You see, some mercury stays back in the pores. So that is called the retention factor. How much of mercury is retained in the pores? And why is mercury retained in the pores? Because the pores are not of the same size, whereas the basic theory of MIP assumes that all the pores in your concrete are cylindrical, of different sizes, but will traverse the entire length of your sim. This is what MIP assumes your pores to be. In reality, the pores are something like this, right? Same volume, but different pathways, different sizes. So MIP is never a good method to absolutely quantify the size. But what can you quantify well? The total porosity or the total volume. So any time you write a paper using mercury intrusion porosimetry, make sure that you can comfortably write the porosity, take the total volume of mercury, divide by the total volume of the sample, say that that's your porosity, but never be sure about the pore sizes. You are getting representative pore sizes, There are ways in which you take the pore size diagram, take the derivative of it, take the first peak and say that's a critical pore size. So you can get some representative pore sizes, but never use it for pore size distribution. You are going to be wrong. There are beautiful papers written as to why pore size distribution using MIP is not a reliable quantity. But total porosity, perfectly fine. Critical pore size, one indicator of what a certain threshold pore size is, fairly reasonable. So here is what, so this is the retention factor. The more the retention factor means, the more tortuous. When there is more of mercury that is retained, which means more of mercury could not come out. More of mercury gets trapped. More of mercury gets trapped because the pore size are so very tortuous, so very variable that all of the mercury could not come out. So higher retention factor is an indication of tortuosity of your pore structure. Again, all regular concrete, nothing to do specially with 3D printed concrete, but since we are on that topic, some good information to have about general concrete. So this is your retention factor when you look at um, your cast concrete was, you see higher retention factor in cast concrete in all those cases, right? Higher retention factor meaning higher tortuosity, which means in printed concretes there are preferential directions where pores can empty out quickly, like what we have seen before, the layer effects, the filament effects, all of that. So retention factor is a good way to find out the tortuosity of the pore structure. So here are some good ways of looking at what the transport properties are. Now, we do what is called a non-steady state migration. Have you heard about that test? A migration test? Okay, so rapid chloride permeability, all of you have heard about it, right? Migration test is the bigger brother of RCPT, which takes off some of the drawbacks of rapid chloride permeability test. What you simply do is to do the test for a longer duration of time under a lower applied voltage. What did I tell you the problem with a higher applied voltage is? Temperature, joule heating, right? One of the problems is joule heating. So that is because of your higher voltage. So what if I apply a lower voltage? Voltage is your driving force, right? So lower voltage means the ions will be driven through the structure slower. So because I am driving slower, what will I do? I will take long time. Instead of 6 hours, I will do 24 hours. I'll drive slow. I will get there later. No problem. I'll still get there. But I'm driving slow, meaning I have no accidents, right? I don't have a higher joule effect. I have lots of other microstructural problems. I don't have it. So you do this test called a non-steady state migration test. Now, why is it non-steady state and why is steady state? If we get into it, then we won't end it today. So this is a non-steady state, which means you're never achieving steady states with respect to distribution of ionic concentrations within the specimen. Okay. So you have this test where you push chloride ions through the specimen. After 24 hours, you axially split the specimen, spray silver nitrate on the specimen. Silver nitrate, if there are chlorides, becomes silver chloride. Silver chloride is your white precipitate that you can see there. See those white precipitate of silver chloride? And you see these preferential direction of silver chloride. What are those? Those are your layers, interfaces, right? You see silver chloride coming through your interfaces much faster. And in this direction, for example, in a higher layer height, you see silver chlorides have come completely through. What does that mean? Your chlorides have penetrated all the way through. I have only a 50 mm specimen. If I have penetrated all the way through in 24 hours, I don't know at what time in that 24-hour range it got penetrated. I can't calculate anything, right? So we simply ignored because it's very highly porous in that region, you ignored it. But in the rest of those directions, you can find out depth of chloride penetration. So it's really high in this for 13 and 20 mm. The rest of it is all small. And direction 2 and 3 has very smaller. So you can see smaller levels of uniform penetration on the, you see this uniform penetration on the surface? Only that much of penetration, only that much of penetration, right? So and then you can use some equations to find out what your migration coefficients are and you can find out migration coefficient as a function of different directions. You want, if it's uniform, you want it to be same, but these values are typically much higher than conventionally cast concrete. You see where the cast concrete value is here, all of these values are higher. So you can find out what your transport properties are this way. Also, you can look at, again, I showed you this picture. These are all your interfilament defects, right? All of those are interfilament defects. So layer height and print control must be monitored. As layer heights increase, larger interfilament voids. Voids, when the direction of measurement of conductivity render higher pore connectivity, you can't really measure the idea. Okay, the next thing is plastic shrinkage. We kind of dump shrinkage also into a durability characteristic right now because there's not much of other durability issues that we deal with. You can see cracking. I showed you this picture earlier. And what is plastic shrinkage primarily due to? Evaporation of water from the surface. Evaporation is dictated by surface area. Higher surface area, faster evaporation, right? So you will see that. So this is time, and you see how the plastic shrinkage strain starts to develop at early ages. So here are some digital image correlation methods for early age shrinkage and plastic strain. We'll show you some more of that. So this is some of Aniket's very recent work where we have looked at effect of restraint on shrinkage, not just along the layer build-up direction, but also in the transverse direction. If you start to build up multiple layers in different directions, so we've used digital image correlation to find out what the shrinkage strains are. So basically, what the idea is, your substrate is restraining the layers in this direction, correct? The substrate is restraining this layer is restraining this layer. You see all of that? So the restraint will be very high here, and the restraint will be almost negligible there, correct? Now, strains by themselves are not a problem, correct? Shrinkage by itself is not a problem. What is the problem? Restraint that causes cracking is a problem. And cracking is caused, stresses are built up because of restraint. If I leave a piece of concrete free to float and move in whichever way it wants, it will happily do what it wants, will not crack. Cracking is because I'm holding it to one shape, holding it to one place, holding it in one direction. Then it wants to move, you're not letting it move, it will crack. So restraint is one of the bigger reasons. Now, if you look at building up filaments side by side, I understand that this filament will restrain the next filament from moving. So there is an interfilament restraint effect also, not as big as the restraint from the subbase and this layer, but there is some restraint there also. So how do you quantify that? So he came up with a nice way of quantifying it. So if you do a single filament and quantify the shrinkage strains at early ages, plastic shrinkage, very early age, 24 hours. So after that, we don't care. We're just doing it for the 24-hour strain. So this is a single filament. You build up 4 layers. You use DIC. Where is the DIC picture? So you use digital image correlation. You build up 4 layers. You make sure that you can speckle it. Again, there has to be some subtle ways of speckling it very early. And when it sets, you have to do another speckling. Correct? That's what you did, right? When it sets, you have to, because the color changes, the contrast changes, you have to speckle it once more. You do all of that, but you can get the strains as you build up. You see higher strains because of the overburden pressure from these layers. So what you can get is the shrinkage at different layers as a function of time for different mixes. And this is for one filament. This is for 2 filaments. And then if it's one filament, so this is your strain after 24 hours. That's your observed strain after 24 hours. DIC will allow you to monitor it completely. If you're doing it in a prismatic test or whatever, you can do this only after you take it out of the mold. So you will have some time that you will have to spend. Right. So then what he did was using restraint along z direction. You take the observed strain, correct it with the restraint coefficient z direction, take that value, correct it with a restraint along the y direction, which is the filament direction, and then extract the free shrinkage. If it's single filament, you just need one step. If it's multi-filament, you need two steps, one in the x direction, one in the y direction, in the z direction, and one in the y direction. So simplified way of doing it, mechanistically consistent way of doing it, and you can quantify what those restraint coefficients are. They're all theoretically derived from mechanics principles based on normalized thicknesses or normalized heights. And then eventually what we'll have, if you do all this normalization, whatever number of layers, whatever number of filaments, doesn't matter, you will converge to one value, that is your intrinsic shrinkage of the mixture, which is dependent only on the mix proportions and the exposure condition. So restraint effects are completely taken out. So what are those restraint effects? So you'll see for different specimens, that's your this is for single filament. This is for two filament where only one direction is normalized. After normalizing for this, you get whether it's one single filament or double filament, you resolve it finally to the same shrinkage strain, which is for the mixture. So you can do a bunch of similar calculations, and also you can do you can find out the elastic modulus of the material using, remember buildability, I showed you how to measure stiffness of a fresh material. Remember that? By carefully cutting a cylinder, applying an extremely slow strain rate and doing the stiffness. So you can find stiffness development over time. If I have strain, if I have stiffness, if I have the restraint strain and the stiffness, can I not get the restraint stress? From the restraint stress and the tensile stress, can I not know if it'll crack or not? Right? So here is when our actual specimen is cracking under shrinkage. You can see a crack that's going through the first layer, close-up of that. There is a crack that's going through, and then you can quantify that crack. You can determine the time of first crack. So here is one way where you can predict. So again, as a test method, different mixes, you can quantify which one is prone to shrinkage higher, which one is prone to shrinkage lower. Under the conditions, you can, whatever environmental conditions, if you have an environmental chamber, if you know that I'm going to be printing in high wind velocity, you can do this entire test under that wind velocity, under that temperature, do the realistic measurements and be able to predict the stresses that are developing. So that's one way of doing it. Plastic shrinkage, early evaporation creates negative capillary pressure before setting. That drives plastic shrinkage. So really the mechanisms of why plastic shrinkage happens. Soon after bleeding stops, you have capillary menisci that's forming, and the rise in capillary pressure. Again, very, very fundamentally what happens if you take one capillary, again, it's all about capillary rise. All of you have done this experiment where you dip a capillary in water and see that rises, surface tension, all of that. Same thing. The whole idea of shrinkage reducing admixtures is to reduce the surface tension of your liquid in the system, right? So it's all about surface tension, capillary pressure, and pressure development. No form work, so all filaments are exposed, accelerate water losses. When water goes up, capillary pressure starts to build up. When the pressure exceeds the tensile capacity of the material at that point, it will crack. Strain, stress, and the stiffness will lead to stresses. Geometry matters. Thin films amplify early capillary pressure under the same drying demand. And then you can do final analysis if you want of these capillary pressures and see what happens with cast concrete and 3D printed concrete. Why do I have no pressure lines in these sites? Why do I have nothing here? Because there is no evaporation from that side. It's all sealed with the formwork, correct? Whereas in 3D printed concrete, you have flux lines on all sites, which means the rate of evaporation is much faster. And you can do, again, very simplistic boundary conditions for a 3D model or a 2D model, where you can calculate stresses that are built up, capillary pressure distribution, and how moisture loss creates cracking. Strain measurements, several ways of measuring strain. There are non-contact strain sensors. There is DIC measurement. You can put in humidity sensors to find out the rate of water loss. several different ways of doing it. Growth of cracking. When will you see cracking along the length of the specimen? Restraint based ideas, very similar concepts that we talk about, right? And where does interlayer zones crack even without bigger external restraint? And cracks will open faster because the zones are anyway weaker zones. They have very low mechanical property, therefore they will crack much faster. Chemical and acid resistance, again, this is, people have done this on 3D printed concrete. You could have done it anywhere. It's exactly same mechanism where they immersed printed and cast mortars in sulfuric acid. Surface deterioration, mass change were noticed. Again, to show that there is deterioration. Interface will accelerate it a little bit more because penetration of acid will be faster through the interface. Same ideas that we talked about, the behavior, whether it's normal concrete or 3D printed concrete, are not very different. So chemical acid resistance, freeze thaw behavior. Freeze thaw is a function of water freezing within the smaller pores and creating pressure. The smaller the pore, higher the pressure, and therefore you can have, if you are in a freezing and thawing zone, even in your 3D printed concrete, in your bulk zone, you need some air entrainment to control freezing and thawing. If not, the layer interfaces, which are already weak, will crack and burst out very quickly. So again, commonsensical things that you need to do it. Again, very similar results that they have found after 100 freeze thaw cycles. So eventually, layer height, printing speed, path strategy all have influence on interlayer compaction, pore connectivity, moisture gradients, all of that. Early age evaporation, capillary pressure driven shrinkage, restraint induces cracking, cracks increases permeability, permeability increases the ingress of deleterious ions. If you have steel, those ions cause corrosion. That more makes it crack more. The whole process, the cycle continues until the damage is complete. So this is a very, very quick summary on durability. There's not much of work that is done on durability of 3D printed concrete. I'm not saying there's lots of work that needs to be done. If there is a need, of course, you have to do it. But the fundamental durability processes, because it is concrete, are not going to be different. The only thing that is different is that you are now orienting the preferential paths of transport. And therefore, if you account for that, that's all you have to have as a difference in 3D printed concrete. The otherwise, most of those mechanisms are the same. Questions? Very quick overview on durability. Yes. Just to know, like, I get it for the explain the going up. The internet for also takes how does it affect with layer we can increase and decrease the porosity. So if there is dependence on layer height. Yeah, you will have a dependence on layer height, right? You will have a layer dependence on layer height. How much it will shrink will be dependent on the layer height. So for example, like I showed you, when you have a smaller layer thickness and much more compacted layer versus very large layers where the bulk is much more porous, the evaporation from the bulk will be much faster because the bulk is much more porous. So layer height will influence the rates of evaporation. Yes. So when there are multiple filaments, then the shrinkage will. Yes, multiple shrinkage will be lower, right? Because shrinkage is restrained. The more layers you add, you are holding on. So the middle guy, for example, is not allowed to move by things on both sides. So yes, you will have reduction shrinkage, and that's what his results show, that when you do a multiple filament printing, the measured shrinkage is lower than single filament. I don't know where that data is, somewhere. Okay, here is 6 filament versus 1 filament. Here, look at 6 filament. Here it's 0.9. Here it's about 0.3. Right? This is 6 filaments. That's 1 filament. So yes, you will have difference in shrinkage, but that's because it's not allowed to move. Right? Shrinkage strains are lower. Yes. Other questions? All right. If not, we'll go to the next topic, and then another half an hour, I will stop after that. No more questions, right? So, shrinkage, durability, if you have anything, feel free to ask Aniket, Sahil, whoever. Those are the guys who did the work. Uh,